Here we go. All right. So you should always feel free to use a calculator. But at the beginning of the year and every once in a while I'll say things like, I do want you guys to know what the shapes of these graphs look like. Okay? And that doesn't mean that you have to know exactly what each function out there looks like. But I want you to have a general idea of what they could potentially look like. Okay? And there's a couple tests that we can go through in order to get that straight. What we're looking at today are polynomials of higher degree. And higher meaning more than 2, really. Because we used parabolas. We had that whole section on quadratics. And so that was all with x squared. Degree is the biggest exponent going on. Like, remember that kind of stuff? All right, so we're talking about 3 and up. And I don't have a calculator that I can get to on this that makes any sense. So I guess you guys are just going to have to trust me. But this section starts on page 218. 218. And, we've talked about polynomials in other math classes. And, usually we refer to them when we're talking about trinomials usually, right? We say, okay, there's a monomial, which is 1, binomial, which is 2 terms, trinomial, 3 terms, and then we call them polynomials, which means many terms. But in the book on 218, they give you a couple more definitions about things going on, okay? And so this is kind of a cool section because it's really a lot of these terms that we're going to talk about today end up showing up in calculus. And so this is like a true pre-calculus section. Okay, none of them are like anything like too crazy though. There's a little bit of notation we got to get over. But then on page 218, the first thing that they talk about is a polynomial must be continuous. Okay, and so like that would be continuous. There's no breaks. That is not continuous. Is that fair enough? Right, so polynomial, not polynomial. All right. Another thing that they talk about is smoothness. So polynomial must be smooth. Is that the word they use? Or is it they use smoothness? Yeah, they kind of use smoothness. All right, so for instance, see how this is a gradual turn? That's smooth, nice and rounded. Okay, smooth. This one, and this is one that we look at a lot lately, that is not smooth, right? It comes to a jagged point. And so this is just, my attempt at the absolute value function. So the absolute value is a function because it passes the vertical line test, but it is not a polynomial, and it's because of this corner. And this corner and continuous, those two ideas are super important in calculus. And we can do things like take the derivative of that one, but not this one. At least at that vertex. Okay, so like I said, pretty important stuff, but pretty easy to identify. So that's what they're saying a polynomial is. And so now what we want to talk about are shapes. Okay? So let's talk about polynomials with even degree. And we're only going to look at one term. So for instance, we're going to look at this one. And we know what that one looks like. So what's that one look like? Yeah, right. It's a parabola. That looks, that was close to that. Like that, right? Something like that? It's kind of close to that. We'll try that again. Okay, so is that okay? So I'm going to do another even one. I'm going to do it in red. I don't know how it's going to show up. but it looks like, boy, it's hard to do on here. It looks like that. And then, no, the color's not maybe coming up for you guys. I'll do it in green here. Let's say, that should have been a g of x, but that's okay. So let's say g of x is x to the fourth. And then that one would look like something like that. So now there's two things that are going on, and we're going to, like I would like to have you guys do it on a calculator, but I can't do it on here, so we can't really see it. But what is the first thing that you notice about, I messed that up. You guys are supposed to catch that kind of stuff. Oop. This is, what did I say? Did I say a fourth when I wrote it? Yeah, sorry. Like, I guess instead of sixth, yeah. Sorry about that. I just get so carried away. You know, my blood's flowing so much better now. I'm warm.
What if it's a decimal?
What?
What if it's like a decimal?
So I don't know. We'd have to play around with that. I'm not sure the answer to that. Let's see. What would they do with that? You would probably break that apart. So like if you had, let's say we had x to the 6.5, you would probably write that, because like your exponent rules, you would probably write that as x to the 6 plus x to the 1/2. And so then the degree of this polynomial would still be to the 6th. I did that wrong. Man, what's going on today? There'd be times. It'd be times right there. What's happening? So maybe that wouldn't be. That's a good question. I don't know. That's a good question. I don't know how the degree would work out with that, like with what we're talking about today. And maybe it wouldn't. Maybe it would just be, we'd have to treat them differently. Back to this. All right, so what do you notice happens as we increase the degree? What's happening? Yeah, it got skinnier, right? Now, before we were doing that, we were multiplying it by a to make it skinnier, right? We'd multiply it by some number bigger than 1 to make it skinnier. Why, then, is this getting skinnier when all we're doing is messing with the exponent? Yeah, right. So for the same x value, so like, right, let's just talk about, like if it was x to the second, or x equals 2, then f of 2 would be 4. The other f, that should be a different letter, would be 16. And then finally, 2 to the 6, what is that? That's like 64. So right, just at right 1, 2, right, all of a sudden we're all the way to 64, because that's how raising something to a power does, right? So then we also have this situation that's going on that you can't really see with the way I graphed it. So I'm going to pretend I'm zooming in, like on the calculator. And I'm only going to look at like that's from one to negative 1 to 1, okay? So then the first one, what color did I do the first one? Black? So let's say the first one, right, they all go through this, right, because 1 raised to anything is 1. So let's say this is our first one. Oh, that was pretty good. So then what happens is, I think red was the next one. So then it still goes through here. It's a little steeper now. That's hard to do. But what ends up happening is, well, let me try again. What happens is it looks like it stays on the x-axis a little bit longer. Why? Well, think about like what we're doing. Okay, so then the green one would also go through these points, but then be a little flatter still. So if the green one climbs faster when we get to bigger numbers, why is it flatter when we're plugging in values between -1 and 1? And so to get this straight, give me a nice easy one to work with. Like, yeah. Yeah, a tenth would work. Yeah, okay. So let's say we evaluate the first f at 1/10. And so then we do 1/10 squared, and that would give us 1/100, right? Well, then the next one was red. So then if we did that to the 10th, then we do 1 to the 10th, or 1/10 to the 4th, and then we'd have so it's not growing very fast because we're dealing with fractions, right? Then all of a sudden it takes off. And so then that would be the same with that. Is that okay? All right, so let's stick with the even ones. So let me move down and give you another thing to look at here. So is it okay if I say that represents any polynomial to the even power? Can we say that? So can we say that this can represent anything in this form? Okay, that maybe it gets flatter here, right? Maybe it gets steeper as it goes up, but basically they all look essentially like that. Okay? So then first question is, what if I wanted to flip this over the x-axis? So write a, right, it still has an a. We could write g of x, negative x to even, like this. It would look like this, right? It'd just be reflected. What if I wanted to not reflect it? What if I wanted it like over here? How would you do that? Let's call that 1, 2, 3, 1, 2. Let's call this 3, 2. X minus, right, because it's in the opposite direction. Even power, whatever the even power is, plus 2. So all these rules are the same, just like they always were, okay? So we're almost done with the even ones here. So let's look at this again. I think we can do this all at once. All right, so we have two different situations here, yeah? We got f of x is x to the even power. That would be the black one. And then the red one will be g of x negative x to the even power. Is that okay? All right, so I'm going to introduce some notation here that you're unfamiliar with probably. But it's a very simple thing. It's just an arrow. And then I'll do it over here the same. So this is read as x approaches infinity. Or like you could think of it as x gets closer and closer to infinity. Or if you're thinking of the graph as x goes way out here. Okay? Hold on one second. And so then the question ends up becoming, what does f do? Or what does g do? So looking at the black one, as x gets bigger and bigger and bigger and bigger and bigger, what is y doing? It's getting bigger and bigger and bigger also. So in fact, it's never going to come back, and it is also going to infinity. Now when a is negative, like over on the red, it goes to negative infinity. Good, yeah. Is that okay? So I'm going to go down to finish this off, and we'll jump back up and down, right? So then we also want to know, so this is the first one. So as x goes to negative infinity, what does g go to? And then when over here, right, this is together. So then as x goes to negative infinity over here, what does f go to? Okay, so, oh boy. Mackenzie, what's going on here? Yeah. Well, you guys know what it looks like, for goodness sake. All right, so then the black one up here, as x, right, this is negative infinity this way. What is the black one going to? What is it? Yeah, it's a positive infinity. And then when we're going in the same direction, what's the red one doing? Negative infinity. Is that okay? So this idea is called end behavior. And what's pretty cool about this, like I said before, is this is like the first thing that we've seen that is talking about something called limits, which show up in calculus. And so then, if we have one of these, we could say, oh, that works. Right, so like, our f of x looked like this, right? So we could say, this is the notation that you might see. Okay, and so then this is read, the limit of f of x as x goes to infinity is what? Well, all they're asking is what we just talked about here, right? As it goes out this way, it goes to infinity, and so then you would say, well, then the whole thing is going to infinity. Okay, but all you guys need to know is this end behavior stuff. So you need to know, because this is going to be on your quiz. This is like part of the quiz. Okay, so you know your parabolas, check. Do you know these? We're almost done. Okay, so, right, you're going to have some kind of statement, right? X to the fourth, x to the eighth, whatever. And you're going to be asked, as x goes to infinity, what does y go to? And now, we only have one term. We keep looking at this one term. Yeah. But x to the fourth could look like this. But notice it's even, right? This is even. Now you'd have to have more terms, okay? But I'm just saying if the biggest degree is 4, it could do something like this. But still, the answer to what's going on at the end as we go super, 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 super far off to the right, well, it's still going all the way up. And if we go super, super, super far to the left, it's still going all the way up. How's that? Does that feel okay? All right. We're almost done. And all we got to talk about is odds now. So everything's exactly the same idea. But now let's think of Let's think of these. So again, these are just simple ones, nothing else going on. So the zoomed out version, x to the third is going to do something like that. X to the fifth will be steeper and then flatter. And then x to the seventh will be steeper and flatter again. Okay, so they have the same kind of properties as they do, and for the same reason, right? If you're raising a fraction, anything between -1 and 1 to bigger and bigger power, it stays smaller and smaller and smaller for longer. Is that okay? All right. So let's do this 3 times then. So if we have this function that is odd, as x goes to positive infinity, y goes to positive infinity. And as x goes to negative infinity, y goes to negative infinity. Is that okay? All right. So let's flip this thing around. Right, so then we're going to have, right, it just reflects over the x-axis, just like it always does. Well, that's basically what it is. Okay, and so kind of before I go on, like, you know, I just thought, this is what I want you to be able to think of. Like, because there's going to be other things going on here. Okay, they're going to have other terms. But if you can look at the first term, you know, the sign of the leading coefficient, which is the thing with the biggest exponent, and what if the biggest exponent is odd or even, then you can have this picture in your head, and that's the picture I want you to have. Okay, or maybe it kind of goes up and down, but we'll get through all that stuff too. Right now we're just talking about, it basically does this. Okay, so then again, let's look at, in this situation, as x approaches infinity, y approaches negative infinity. And when x approaches negative infinity, y approaches positive infinity. Okay, and then so then the book refers to this idea of a being positive or negative as the leading coefficient test. So we're doing like this leading coefficient test, which all you got to think of is it positive, is it negative? What's the shape? Excuse me. And am I an even or odd power? So you're totally going to get that kind of stuff on the quiz. Absolutely. Is that okay? All right, so then let's flip up to page, where the homework is, 227. You have to do 1 to 21 odd. But I want to go over these, like the pictures, just as a generalized thing. Okay? See, let's kind of reinforce the shapes of things here. So part A, right there on 227, we're not doing these problems, you're just matching them up. And by the way, there are 4 IXLs that go with this section. One of them is exactly doing 1 to 7. Okay, you're just identifying, you're just matching. You won't be able to do them all until we get to 47, but we'll do that here on Monday probably. So A, all I want you to do is say, is it an even or an odd on A? Say it again. He says even. Why is it even? Because they're both both are going to the same place, right? They're both going to negative infinity, so it's going to be even. If they're both going to positive infinity, also even. Is that okay? So then is the coefficient positive or negative on this one? All right, so it's already reflected, so even power, negative a, we'll just call it negative a. Is that okay? Because it's going to both to negative infinity. All right, number B. All right, does all kinds of weird stuff. It goes like this, and like that. Is that going to be even or odd? Odd. Why is it odd? Yeah, they're going, one's going to negative infinity, one's going to positive infinity. Is A positive or negative? It is positive, okay? So, and this is the stuff that you may not understand yet, but, right, they all basically do this shape where they go from, they're climbing and they keep climbing. That's negative. Or I'm sorry, that's positive. Odd and positive. Is that okay? Right, the original one looked like this. All right, so jump down to D. Is that going to be an even or an odd power? So, right, you're looking at the end behavior. You're going to say even if they're both going to the same place, odd if they're going to opposite places. So even, is it negative or positive A? Positive A, good. Part E, is that going to be even or odd? Odd, is it going to be positive or negative? Negative. Okay, so is that okay? All right, so then you're matching them. 9 through 11, you are going to, you're just translating this around. You're shifting it, just like you did on those IXLs. Right, nothing new really there. And then 13 to 21, they're basically doing this again. Ideally, you just look at it and you know. But if you don't, then you graph them. But left hand, they say determine the right hand and left hand behavior. Okay, so this is over here, right hand. So right hand is when x approaches positive infinity. And then left hand is when x approaches negative infinity. All right? All right, 1 to 21 odd is all we're doing on this one.